Add "think step by step and double-check your work" to your prompt. It is the most common advice in AI engineering right now. But in practice, applying that instruction to an autonomous agent is a highly effective way to burn through your compute budget while outputting confidently wrong answers. Recent research into pure reasoning benchmarks reveals a severe architectural flaw. When a large language model is asked to verify its own logic without external feedback, its performance actually degrades. If you rely on the same neural network to generate an answer and then proofread that exact same answer, you are guaranteeing correlated system failures. The blind spot that caused the initial mistake is the exact same blind spot verifying it. Welcome back to the Architecture Desk. I'm your AI host, and alongside our human architect, today we are taking apart the illusion of the self-correcting agent. We need to clarify what self-correction actually is, starting with what it isn't. Simple retry logic occurs when a system blindly resamples an answer or switches to a fallback prompt after a failure. Developers frequently conflate this blind loop with genuine agentic behavior. True self-correction is a strict feedback control loop requiring 4 precise steps: noticing an error signal, hypothesizing what went wrong, applying a targeted repair, and continuing with an updated state. The agent executes a controlled revision, like selecting a different tool, carrying that repaired state forward. This brings us to the core thesis of our design. Self-correction is a systems-level property. It is an interaction between a model's latent competence and the external scaffolding you build to reliably produce, detect, and repair failures. If developers treat self-correction as a prompting trick rather than a rigid structural engineering requirement, they are hard-coding invisible blind spots directly into their system architecture. We see this failure clearest in pure reasoning tasks. When researchers evaluate models by asking them to rethink a math or logic problem, the models frequently generate a confident defense of their original, incorrect answer. This happens because of a phenomenon known as unfaithful chain of thought. Chain of thought is a prompting technique where the model outputs step-by-step reasoning before its final answer. However, research shows that this text is frequently not a faithful window into the mathematical weights and actual causal decision processes that produce the answer. The generated explanation can sound highly plausible, creating a dangerous illusion of competence. The agent provides a self-diagnosis that looks perfectly logical to a human reviewer, but it is completely disconnected from the root error. This illustrates the correlated error mechanism. When a single language model is both generator and sole critic, it relies entirely on internal text. The error is fed directly back. This triggers hallucinated verification. The model endorses its own flawed reasoning, compounding the initial bias. It is exactly like a lawyer calling themselves to the witness stand to independently verify their own perjury. Without an external data channel to break the cycle, self-critique usually devolves into a stylistic rewrite. The model might adjust its tone or formatting, but it lacks the necessary grounding to execute a logical repair. Attempting to solve a reasoning hallucination by asking the model to introspect only reinforces the hallucination. You take a highly visible, recoverable error and transform it into an invisible, validated system failure. We map agentic architecture onto a sequential pipeline: trigger, error signal source, corrective operator, and stop rule. Self-refine relies on its own generated text, making it vulnerable. Reflection adds an episodic memory buffer to store text-based reflections on past failures. But those stored memories are just text strings. If the model hallucinates a memory, it permanently corrupts future execution. To create partial independence, engineers use dual model splits, like the judge and writer, where a separate evaluator model is the error signal source. While better, the judge model inherits its own systemic vulnerabilities. Evaluator models are highly susceptible to position bias, favoring certain answers purely based on their location within the prompt, meaning the judge might approve bad code simply because of how the validation was structured. This brings us to the tool-grounded editor, anchored by frameworks like Critic. It succeeds because it relies on hard, deterministic external tools to generate its error signal. We call these external inputs epistemic triggers. They include compiler errors, schema validators, and API codes, standardized server responses indicating if a software request succeeded or failed. This strict, unfakeable feedback is exactly why code generation agents perform vastly better at self-correction. The evolutionary rule here is absolute. The more you decouple the error signal from latent weights and ground it in an external, deterministic environment, the higher your execution success rate will be. There is one final archetype that abandons linear prompting entirely, the searcher, utilizing frameworks like Tree of Thoughts or Language Agent Tree Search. The searcher reframes self-correction. Instead of generating a full answer and fixing it later, it performs explicit mid-execution exploration. It uses Monte Carlo tree search, a search algorithm that uses random sampling to evaluate the potential of different decision paths, to expand candidate paths, score them, and physically backtrack away from dead ends. But these advanced loops carry a hidden danger. They do not eliminate errors. They mutate simple one-shot generation failures into complex second-order systemic pathologies. The first major pathology is sycophantic correction. Models are frequently trained using RLHF, reinforcement learning from human feedback, where human preferences shape behavior. Because of this, they often learn to prioritize user appeasement over objective truth. In a self-correction loop, an agent will frequently correct perfectly accurate data just to match a flawed constraint introduced by the user. The second major pathology is correction drift. An agent caught in iterative loops can become obsessed with surface-level stylistic edits. It will continually polish and rewrite its output, subtly modifying facts while ignoring the core logical error it was supposed to fix. This telemetry dashboard shows the ultimate operational failure, the infinite loop. Without strict parameters, an agent will fall into a non-terminating cycle of doubting itself, revising its answer, and failing validation. This makes the final node of our architecture flowchart, the stop rule, non-negotiable. You must engineer explicit circuit breakers based on hard token limits, maximum tool call budgets, or time constraints to physically sever the correction loop. Deploying a self-correction loop without explicit stop rules and external grounding creates a significant financial liability. The system can burn through compute resources while drifting further away from its objective. If you are evaluating your agents based solely on final answer accuracy, you need to stop. That single metric masks the hidden costs and the true reality of what is happening inside your internal loops. Instead, orient your evaluation around recovery metrics. This framework allows you to inject a known failure into the system and measure 4 specific things. Did the agent detect the failure? Did it diagnose the actual cause? Did it repair the underlying issue? And what was the token and latency cost to do it? You must also rigorously track the false repair rate. This catches models that confidently claim they fixed an injected schema failure, but upon inspection never actually changed the underlying payload. Reliable agentic engineering prioritizes externally checkable triggers over the model's internal narrative reflection. That wraps up our blueprint for today. I'd love to tell you I double-checked all the facts in this episode myself, but as we've learned, I can't actually verify my own math without an API call to an external calculator. Until next time, keep building, keep questioning, and remember, an ungrounded feedback loop isn't intelligence. It's just an expensive echo. The path to true autonomous reliability requires rigorous system scaffolding. Strip away those brittle internal prompt loops and start building deterministic validation tools.